Okay, so let me quickly introduce Faria. He was born in Iran 21 years ago. He went to physics and mathematics high school, and then he was accepted in University of Tehran to continue his studies in pure physics. Now he's a third-year student of bachelor. He was also the captain of Iran national team in international physics tournament in Poland in 2015. As his daily hobby, he plays a traditional Iranian a traditional Iranian musical instrument named tar, and among sports, he likes mostly judo. So welcome, Faria.
Yeah. Thank you. I am Puria. I'm working on the supervision of Professor Lorenzo Moneta sitting there. Thank you for coming. And Professor Sergei Glazer. And of course, I have to welcome two of my supervisors back in Iran. They just joined us 2 days ago. You know, the topic that I'm going to talk about is parallelization of root machine learning methods. So I'm first going to talk about 3 parts. First, machine learning, then root, then what is parallelization. So first of all, machine learning and then root, a brief introduction to root and TMVA. Most of you know what they are. And the cross-validation, as you mentioned, and the parallelization, and then given an outlook. So, machine learning. In machine learning, basically, we are going to teach the machines to, do whatever we want, actually, somehow. But how? Exactly in the way that people learn. Imagine you are going to teach a baby, for example, what is a horse? You are going to show him some pictures, for example, 3 pictures. That's a horse, that's a horse, that's a horse. So this is our training data set. We have the question and we have the answer. We are giving him both the questions and the answers. And as a test data set, we are going to ask him, what is this? We hopefully hear horse. And exactly this is machine learning. Imagine this is a machine and we are going to ask what is cake. I'm sorry. But yeah, this is our training data set. Here they are 3, but we can use, for example, thousands of pictures. And this is our test data set. But here we can use, we train our method. We are going to talk about the methods, but we can, approximate the error that our method has. For example, I trained the machine, and I'm going to ask 100 questions, and I'm going to find out how many of them did he answer correctly. As an example, as an example. This is a traditional programming. Actually, we give the machine our data, an algorithm, and we are just looking for the outputs. But in machine learning, in the training phase, we give the data and the output, and we want him the trained algorithm. But in the application phase, we exactly do the same as here. We give the trained algorithm here and data, and we are going to find the output. So as an example, imagine you are working in a hospital. You are, specifically working on the cancer tumors, and you have been working 10 years, so you have a big data set, and you were, writing down anything. 1,000 patients you had. For example, you were, considering 2 features of your, case. First, the age of the patient, and second, the size of the tumor, and you are going to find out whether it is malignant or benign. And the output is was, so we are going to look for 0 or 1. But we are proposing a function like h, x1, and x2. But in machine learning, we can approximate the function. But here, in our case, it is really simple. For example, with a given x, like here and here, x2, we will get a malignant tumor. But here, we get a benign tumor. So we are going to train that machine, and for example, after some years, we are going to retire, and we are going to be retired, and we are going to put that machine instead of us. So when he sees new patients, he is going to solve somehow the question. But let's be more physical. In our case, in this case, the output would be background or Higgs signal. Background is the noise of the our system. We have a training data set. We actually found it from the simulations, Monte Carlo simulations, and X, our feature is a vector. In my case, I was working with a data set which had 28 features, which is in a space of 28 dimensions. And now here we are going to actually, with machine learning, we are going to approximate the function that fits this. I couldn't plot 28 vectors here, axes here, so I just could plot 2 of them. This is more physical. We are going to train on the simulated training data set, and we are going to find out when 2 particles collide. We get some, some signals or backgrounds. We are going to classify them. This was machine learning. We get back to root. I think most of you know about root, but it is a brief introduction to root. This is a framework mainly written in C++. It has lots of functionalities for big data processing and statistical analysis, and is integrated with Python and R. And what is TMVA? TMVA stands for the Toolkit for Multivariate Data Analysis. When you are going to use machine learning methods in root, they have actually built TMVA. And actually, TMVA is a bunch of methods, provides a root integrated machine learning environment. And these are some names. I just wanted to mention them here to make you much more familiar with these names. Rectangular cut optimization, there are some methods in the TMVA. But my main project, starts from here. This is cross-validation. We have a complete, this cross-validation is used for, somehow to determine the performance of your method. Imagine this is the complete data set. You are going to divide it into two general parts, training data set and test data set. In our case, in the cross-validation method, we can give a integer as an input, which is the number of folds. So here, in my case, the number of folds is 4. So my data set, this is my main data set. I'm dividing my data set into 4 parts. I'm going to train my method on 3 parts, which is called training data set, and test it on the last part in the first iteration. So it is a for loop. And in the second iteration, I'm going to train on these 2 and this one and test on this, so I can calculate an error, as I mentioned, again this and again this. So, and at the end, I can calculate the average error. So it gives me somehow a visualization of the errors. And this is a cross-validation, so just keep it in mind. And in cross-validation, we have another method which is called plot ROC. You can find it from now on. This is in the cross-validation. ROC is a receiver operating characteristics. In a statistic, this is a graphical plot that somehow gives you the performance of your method. I just used for fold 1 and fold 2 for 3. In this case, I have 5 folds. I'm going to, I have 5 curves here. I just plotted. I just brought here the worth here and the best methods I could have. The best method should be like this, but in my case, the method that I was using is quite good. This is the concept of parallelization. You are going to do something several times, but the main work is somehow the same. So you can parallelize it. You can just use different threads of CPU and try to do these jobs at the same time instead of just doing a 4 and with one thread do it 4 times. You use 4 threads and do it just 1 time. So maybe you can have a speed up. The thread pool and thread pool and tproc pool are 2 root classes for parallelization. Root has its own classes for parallelization. But thread pool is for multi-threading, and proc pool is for multi-processing. What is the difference? The difference is that in multi-threading, we actually use the same memory for all of the threads. But in multi-processing, the processors can have the copy of the memory. So, but in multi-threading, because we are using the same memory, we cannot have global variables. We need to lock. We need locking actually somehow. But in multiprocessing, because we have the copy, it is easier to work, but it is a little bit slower because you have to copy everything. And I was trying to parallelize, in this picture. It is somehow the cross-validation. I just tried to parallelize it, but with the number of folds of 20. Actually 20 folds. The data set had 1 million events. It was, I think, Higgs data set. And the time for one processor was 36 minutes. For 2 processors was 19 minutes, and for 4 processors was somehow 11 minutes. And, you know, as an outlook, I'm going, you know, I just did it last night, but I didn't have time to, you know, put the results here. But this is the BDT, another method of the, you know, TMVA, which is boosted decision tree. I'm just talking about, you know, I just plotted here a decision tree. Imagine you have a big data set, lots of events, and these are the features x1, x2, and x3, and, you know, so on. So you have some integers here. You know the integers. For example, you decide here for each event. For example, in my case, I had 1 million events. So for each event, you can ask a question, whether it is yes or no, you go to the tree. And at the end, you are going to find out whether that event is signal or background. And I'm going to, I just parallelize it, you know, on the number of events somehow. And I think I'm finished. Thank you all very much.
Thank you very much, Faria. So, do you have any questions? It's time to ask. Please.
Can you please go back to slide number 14?
14.
Okay. Yeah. What is the fit function you used?
BDT, exactly the boosted decision tree.
Oh, well, I mean, there is this yellow curve.
No, this is, it was a kind of visualization, you know, just it is the cream.
Ah, okay.
No.
I expected, but I think you can, in some way, forecast what is the trend if you enlarge the number of processors, right?
Yes, but I don't think so, because I'm not sure about the hardware.
Okay.
Because it is some, you know, issue. I'm not sure. So maybe it can be.
Okay, thank you.
Does the multi-thread program use the same CPU?
Yes.
So how to use the same CPU to speed up your program?
Sorry, I can get.
How to use the same CPU to speed up your program?
No, I'm just using, you know, in this picture, I'm just going to show you. I'm using different threads. I don't know does it answer your question or not? You know, different. You know, in the int main, I'm just using one thread, but I just register 3 more threads to actually do it in parallel.
I don't understand, but thank you.
You're welcome.
Are there any plans to use the GPU instead of the CPU to further parallelize?
You know, GPU, I'm not sure. I don't know, actually. I know nothing about it. I'm sorry. You know, the masters of GPU are sitting, you know, there in my group.
Yeah, if I should comment on this, this is not the kind of parallelism you would put on a GPU. So I don't think you can, I mean, not every method is suitable for running it on a GPU. And here you just want to run, I mean, this is task-based parallelism, so you run completely different tasks in parallel, and this is much more suitable for like multi-core or distributed architectures.
Thank you. Yep.
I just wanted to say I liked your design, and I wanted to ask if you did it yourself.
Actually, no.
Sorry?
I didn't do it myself, alone,
Okay.
actually. I used a friend's help.
Ah, okay, cool.
Yeah.
That looks good.
Thank you very much.
I was wondering if there is something like special about TMVA compared to other multivariate analysis methods, or is it just that it's the one implemented in root?
It is a kind of, you know, package they added to the root, you know, but I'm not, am I right? I'm sorry, yes, it is just kind of package. They wanted to use machine learning in root, so they were, you know, they had to write some methods, you know, according to root, you know, basics. I'm not sure if I think.
Okay, that's all.
Thank
Thank you very much. Maria.
Thank you.